Cool. Hope everyone's having a good day. I'm also going to go live on YouTube. I don't know why. I think it seems like it's a better quality. I guess for people that are on the Google Meet, how is the quality right now? I'm not using the portable camera that I have. Like, how is the quality with this right now? Quality's not great. Okay. If quality's not great, I'm going to be on YouTube live. If that's a place you want to see, if that's better for you, it seems like the quality of that camera is substantially better. So. And that way, once every class is recorded, I never have to teach again. Yes? All right. You
should be the guy.
Day by day.
I'm going to go live on YouTube. No questions.
No questions.
I was thinking to say live. I'm going to go live. Enjoy that. You could be a sleeper.
Yeah.
In Kentucky or something.
I could be like you guys when you're virtual. I'll be like you guys when we're virtual. Just put my avatar up, right? Yeah. Go from there. So a few things as I'm pulling things up. I saw someone ask a question just for me to go over a question in AP Classroom, so I'm trying to pull that up. I have opened up progress checks in AP Classroom, right, for both forces and circular motion, okay, Unit 2 and 3, as well as the free response questions. I believe on Schoology, I posted the link to the scoring guides for the free response questions as well. So that's something we can study, okay? Free response questions are going to be on Friday, all right, starting at 9:25, right? 9:25, you'll have access to them. You have to then email them back to me by 10:25, right? And just take a picture and shoot me an email. You don't have to send it through Schoology. We'll just take one step away from the process. Everybody's cool with that? On Thursday, right, we'll do all multiple choice questions, right? 25 multiple choice. Most heavily weighted probably towards forces. Okay, so that'll probably be the biggest chunk. And then circular motion and one-dimensional motion, as well as, I guess we didn't have two-dimensional motion on there as well, like projectile motion, right? So that'll be there as well, right? So projectile motion, circular motion would probably be a little bit heavier weighted than one-dimensional motion, right? But obviously all of these things kind of go together, right? They kind of go together, which is somewhat nice for AP Physics 1, but also somewhat difficult because sometimes you don't know like what approach you should have, but they're all on there. Question?
So are we really going to be like solving much for the multiple choice?
So multiple choice, it's going to be
just conceptual stuff.
It's most, I will say, I don't have it made yet, right? But most of the questions are conceptual, right? There are ones, just like in the first midterm, where you have to do calculations, right? But most of them are going to be conceptual, okay? And I will say for most of us, this is going to be, we're going to be taking the test at home, right, on our own. So obviously there's opportunities for you to use whatever you want, okay? But this is more of for you to see like where you stand, right, on these topics, okay? Remember, you have test corrections as well as you have a curve after that, right? As well as you have a group midterm on next Monday, which usually helps boost your grade, unless you're not here and you'll be excused from that, right? So I would really encourage you guys, right, to, go by the honor system, okay? The things that you can have are your calculator and your reference sheet, right? Have your reference sheet out because that's obviously what you're going to have on the AP exam, but use that as you're working. So like on Thursday, as you're working, you have your 25 multiple choice on Schoology, right? You should have scratch paper that you can work through with your score, with your reference sheet right next to it, right, and your calculator. And honestly, I would also just keep track of what answers you have, because that's going to help you on your group midterm on Monday, is actually knowing what questions or what you scored or what you
Monday.
Group midterms Monday
At the normal time.
Yeah.
Okay. So what are we do my best. What are we doing Friday?
Friday is the free response questions.
Right. Okay.
Yeah. So Thursday, multiple choice questions. Friday, free response questions. Right. Friday's free response questions most likely will be on either projectile, forces, or circular motion.
Wait, what was the first part you said? Sorry. Free response.
Free response questions are on Friday.
And
2 free response questions. Right. Most likely they will be on either circular motion, two-dimensional motion, projectile motion, or circular forces. Okay. So, or a combination of some of those.
So it's a total. So we're going to be answering 2 free response questions.
Yes.
Or okay,
yep. 2 free response questions. One's a 20-minute question. One's a 25-minute question. Right. So that's the 45 minutes of the class period. Okay. Essentially, we're taking half an AP exam. We have 2 days. In that 2 days, that's an hour and a half. Right. You have typically an hour and a half for multiple choice questions, and then an hour and a half for free response questions. We have an hour, so that's 3 hours. We're having an hour and a half total. So we're having kind of half a multiple choice and half a free response. So we're taking half of a full AP exam. Yeah.
Okay, so 2 things about the AP exam. Is it like for how many multiple choice questions are there?
Usually there's it's I believe it's 50, but it's 40 or 50.
And how about free response?
Usually 4 or 5.
Okay. And are you allowed to is it 3 hours total, or are you allowed to? You're like, is it? Like,
it's an hour and a half. It's an hour and a half. Like on the actual exam, it's an hour and a half. Multiple choice, straight. You have a 5-minute break or so, and then it's an hour and a half for free response questions.
Yes, it was worse.
That's better.
Especially I'm
it's all.
2 of those in one day. Actually, no, I'm not. Probably not. Oh wait, no, they don't do that. I didn't know. I guess they do.
Hey, Shreya, AP. I'm seeing your question about the center of mass questions in AP Classroom, Unit 2, Part 2. I assume, is that Part B that you're referring to for the questions you wanted to go through? But yeah, so it's essentially half an AP exam that we're going to be taking. Okay. So yeah, going back and looking at conceptual questions from Unit 1, right? As well as the projectile motion conceptual questions, like all of that stuff will help you, okay? As well as in the textbook, and I know you guys don't have a physical textbook, but like on Mastering Physics, there is an e-text that you can look at where in the back of each chapter, there are misconceptual questions, right? So not conceptual, but misconceptual, where they ask the type of questions that most kids get wrong on the conceptually. And they direct questions specifically at those ideas. Those are really good to study from because they really test and make sure you're understanding what your conceptual understanding is. Okay, I think I got to it now. Sorry, I was on AP Physics too. Okay. I'm just looking at the questions. 14, 16, and 17. Okay. So Sherry, this is definitely something that we hadn't talked about in terms of center of mass, but I think we can understand the idea of this. So guys, I'm looking at AP question, and I'll kind of write out the question so you don't necessarily have to pull it up. But I'm looking at AP Classroom, Unit 2. So this is AP Classroom, Unit 2, multiple choice questions, B, number 14. So here's the question. It says 2 astronauts of identical mass are connected by a taut cable. So we have astronaut 1, astronaut 2. All right, we're just going to imagine they are spheres. Okay. They're initially at rest with respect to nearby space station. Astronaut Y pulls on the cable towards herself. Okay, so, and then what's the other one? Astronaut X. Okay, so we have X and Y, right? And astronaut Y starts to pull on the cable towards herself. Yes? Everybody cool with that? Okay, Maya.
Sorry.
Focus here. It's okay. So what the question asks then is, the question asks, which of the following describes the direction of velocity of the center of mass of the 2 astronauts after astronaut Y pulls on the cable? Okay, so let's just think about this. And we haven't talked about center of mass, okay? But the center of mass is like if we were to find a single point so center of mass is the idea of like if I were to balance something, I need to have something balanced by placing support over its center of mass. Mike, can you grab one of the meter rods for me? This will be much easier. Okay. Whereas right now with this, my center of mass is this red tape. Yes. And I can support this and it's going to be balanced as long as my center of mass is supported. Are we cool with that? Okay. Now, a cool thing is if I do this and I try to bring my fingers together, they will always meet at the center of mass due to friction. Okay. And there they meet. Right? Like I'm not trying to move one hand versus the other. I'm trying to move both of my fingers towards one another. But the cool thing is like one finger moves and then the other. Okay? Because look, when I'm like this, yes? When I'm like this finger moves because there's less friction. Right? Because this is supporting more of the center of mass, so the normal force is bigger. Yes? And so this has less friction because there's a less normal force. Once this comes in, and it has a bigger normal force. Now this has less friction, so it can slide. And eventually they meet in the middle, which is really cool.
If you go outwards, if you start moving them outwards.
I don't think so because we're never, like as I move this out, it's never increasing the normal force. The normal force would be less and less and less and less. Yes? So this would never start to have more friction. It only works if I bring it in. Yeah, I never tried. That's a great question. No one's ever asked that.
I guess actually that kind of makes sense because if you're moving it out, you already have one into the center of mass.
Right. Yeah. This is really cool. Yeah. Isn't that cool? It's like friction decides who moves. Yes?
Try.
Yeah, sure. Yeah. Yeah. But the idea then is like same idea with this, okay, is if I put this here, right? If I put this here, all of a sudden my center of mass is not the red tape. Yes? My center of mass is going to be substantially closer. Ooh, this is cool. Yeah? Like my center of mass is going to be substantially closer to just where this mass is. Are we cool with that? If I had both of these, so in this circumstance that this problem is presenting, we'll see if we can do this without things falling off, right? The idea is, where's my center of mass now?
Still in the middle.
Yeah, it should be in the middle, right?
It's just center of mass is just kind of like an average of where the mass is.
Absolutely, right? And you guys have seen like, there we go. You guys have seen like those birds that like sit on the side of a cup. Have you guys seen that?
Yeah.
like little tricks where like you can have, you know, you've seen like where people balance a lot of forks on something where the forks are interlocked, right? And it's because even though there's so much mass outside, they can balance because their center of mass is here. So there's like little things where you could have something that just is barely touching the side of something, but then, you know, it has this big weight over here and it balances because the center of mass is, you know, right here. Okay.
You thing where you take like you take a piece of string and like a weight or whatever, and like a couple of toothpicks, and you set them up so like you've got the one toothpick like this, another that's like barely on the table. You have one that's like this, and then one that goes from here to like here. But like there's a bunch of weight, so somehow it doesn't fall. Have you seen that? I have no idea. Okay. Cool. But it's probably the same idea. I don't know. You kind of lost me when you started describing toothpicks and strings. Yeah. So does everybody agree? Like initially, the center of mass is right here. And this astronaut, equal mass, and then the center of mass is right here. Yes? Cool with that? So then the question asks, what is going to happen? It just went away. Oh, here it is. I think because I'm live streaming, my computer is going substantially slower than it normally would. Too far. It says, describe the following. What is the direction of the velocity of the center of mass? Okay, so here's what happens. Astronaut Y yanks on the string. Okay, what does that do? That pulls X this way, yes? With a force, which means they now have an acceleration that way, yes? Okay. Wait, with the other guy, the guy that's yanking, wait, is the guy that's yanking on the string grounded? Or is he
nope, they're both floating in space.
Wait, then wouldn't he get pulled closer?
Absolutely. If Y pulls on X, X pulls on Y with an equal force, yes? Which means if they're an equal force and their masses are the same, their accelerations are equal as well, right? Boom, boom. So they're both moving towards the middle. So does my center of mass change? No. So the best answer would be the center of mass does not move. Cool with that? 16. Said, two ice skaters, skater X and skater Y, are at rest on a horizontal surface made of ice. So we have our ice skaters. X, Y. Friction between the ice and the skates are negligible. Skater X, who is smaller than skater Y, so big M, little m, yes? Pushes skater Y such that skater Y travels with a speed of 2v0. So they push apart, yes? So Newton's third law says there is a force on Y due to X, yes? There also must be a
Force on X.
Yep, and which force is bigger? They are the same. Because Newton's third law says for every action, there is equal and opposite reaction, right? So F or X pushes on Y, and therefore Y also pushes on X with equal force, yes? Okay? Equal force, how do their accelerations compare? Ooh. Remember, acceleration is F over M, yes? Because F equals ma, yes? F equals ma, yes? So big acceleration, little acceleration. Yes? Question? Okay. So this says then, so this is 2v. So this person starts moving 2v, right? Skater Y travels with a speed of 2v to the right. Which of the following indicates the direction of the velocity of skater X and the direction of the velocity of the center of mass of the two-skater system? Okay, so here's my, my center of mass would probably be more right here, yes? Before they push apart, bigger mass, smaller mass, yes? It's not right in between because they have a bigger mass, yes? Skater X is going to start moving with a velocity in this direction, yes? Greater than 2v, yes? So what do we think about the center of mass then? The bigger object is moving to the right, yes? If the bigger object was moving to the right and X didn't move, what would the center of mass be doing? It'd be moving to the right, okay? If the bigger object didn't move and this person was moving to the left, the center of mass would move to the left. They're both moving away though, yes? But who's moving away faster? X is moving away faster, yes? But Y still has a bigger, right, okay?
Wait a minute, but if
so here's the.
Well, in that case, if you cancel out like the way that they're moving, it should be moving left, right?
What?
Like, because if you've got Y moving and X moving, you're moving in opposite directions, but X is moving faster, right?
X is moving faster, but it has a lower mass.
Should it be moving left?
Y is moving slower, but has a bigger mass. Okay. So here's what I kind of haven't addressed this, but I think these are good questions to bring us to this. So let's look at think about this. This is looking at each person individually. Yes? We're looking at this skater individually. We're looking at this skater individually. Yes? What if we looked at them as a whole?
That's terrifying.
Right? Skater X, skater Y, right? But we look at them as a system. Yes? I know, it's like, what?
It's really creepy when you rub your arms. That's really...
You don't skate with your arms. Okay?
No, do you leave them off the ice?
So if we look at them as a system, here's what's true. Internal, like them pushing each other are internal forces, and that does not affect the center of mass. Okay? And so because these are internal forces, like they're working within the system, the center of mass would stay constant. They would move individually, but the center of mass would stay the same.
Okay.
Yes.
Wait, doesn't the center, wouldn't that still depend on how much faster the velocity of X is compared to the velocity of Y?
No, because their relationship in terms of like their acceleration relationship is always going to stay the same because it's force over mass and force over mass. And their velocity is equal to their initial velocity plus acceleration times time, right? So their velocity is related to the acceleration, right? Their accelerations comparatively are going to be like that. The times that they're accelerating are going to be equal, okay? So it's going to be consistently the same. Does that make sense?
So if the velocity of the person going in the X direction was like 8 times greater than the velocity of Y, it would still stay that same center of mass.
Yeah, because that would mean the masses are that much substantially. Like if this, so the forces are the same, right? Excuse me. And so if this velocity were 8 times bigger, that means this mass is 8 times bigger.
Okay. Does the question say that the masses are relative to that?
It doesn't matter because of this. The forces are going to be the same always. The internal forces are the same, right? For every action, there's an equal and opposite reaction. So because this force is the same, right? If one is 8A, right? If like the lower mass is 1, right, and it's 8A, cool with that. Then to have this I don't really know how I want to show that. I guess let me show it this way. If this is 1, if we had F over 8m, that would be 1/8 a. Yes? So this acceleration is 8 times this acceleration, right? If it's twice the mass, it's half the acceleration. So then this acceleration is twice that. Does that make sense? And then that's the velocity. The initial velocity is 0 for them. Then it's times the same time that's pushing them. Okay? So then the difference of velocity is going to be the same. Fair enough? Okay. You guys good with that?
Yeah.
John, we're good at like dropping it and then first bounce or fly, baby. No. It has to happen naturally. Right? And then 17. Object, ooh, yeah, this is a good one. So this is all, and I apologize, we never covered this, and I don't know if there would be questions on this on the midterm, but this is definitely, it's something we'll try to address more in the future, because it's definitely on the AP exam as I go through questions on the AP exam. The last question says an object of mass m is dropped near the surface of the Earth. So here's the Earth, okay? Such that the gravitational fields provides a downward constant force on the object. So there's, a force of gravity pulling the object down, okay? Which of the following describes what happens to the center of mass of the object Earth system, okay? So if this is the Earth, this is our lemon Earth, okay? If this is the Earth, here is the center of the Earth. Where is the center of mass of this system?
There, the center.
It's going to be just outside the center, right? Like, I mean, literally the center of the Earth, but just outside, we could say, right? In theory. Yes?
Wait, what was the question on the first?
Where is this? Where is the center of mass?
That mass thing on top.
The center of mass would be,
okay.
in reality.
I didn't see the dot up top.
No, it's okay. In reality, like, if this was the center of mass of the Earth, like, the center of mass of the system might be here, right? Like, just outside of that. You guys cool with that? Okay. So the idea is same principle. Newton's third law. The Earth pulls the mass down. The mass pulls the Earth up with the force of gravity. Yes?
Wait, you kidding me?
Yes.
Show what it counting means. It's something.
So we're acting
What
as
if
a
we
force
put,
upon
yeah,
the
like, what
Earth.
if we put
Wait.
all the people in like one spot?
That's a
like,
great-
on top of each other?
Yeah. And then they all jump. Yes? There's a great, I'll shoot out an email with the website. There's a great, like, what if? Because it says all the people in the world, if we could get them packed in, like, really tightly, they would pretty much equal the area of Rhode Island. Right? Yeah. And then if they jumped, and then it goes through, like, if they jumped, and then they realize, like, what happens, and then it's great.
Are we jumping when we, like, 1, 2, 3, are we jumping on 3, or are we jumping after 3?
Yeah, but then
1, 2, 3, jump.
it's really funny.
1, 2, jump.
Because it goes through, like, okay, now everyone has done this, and now everyone needs to go back home. And so the transportation system of, like, getting people to fly out, 7 billion people, and, like, it's like slowly the Earth decays because, or, like, people start dying because there's no. It's really it's very fun.
That's I know what you're talking about.
Yeah.
Yeah.
Okay. Anyway, it's like the worst live stream of physics in the world. We haven't talked about
This
physics
is
at
going to be
all.
the one that gets the most views. Physics teacher gets way off. Starts talking about
The Earth pulls the mass down. The mass pulls the Earth up. Okay. Newton's third law. Those forces are equal. Okay. What is the acceleration of this object? 9.8 meters per second squared. Yes? That's because the acceleration is force over mass. Okay? What is the acceleration of the Earth? Is it the same?
No, 'cause it-
So when I drop this, do you feel the Earth accelerating up at 9.8 meters per second squared?
Virtually
Yes.
nothing.
So is it a lot smaller because of the mass of the Earth is so much greater?
Yeah. It's like force over mass, right?
Yeah, okay, that makes sense.
Okay, force over mass. So my acceleration then is 0.0000000000001, right?
Yeah.
Okay, it's so small. It doesn't matter. It's so small. And this question then says, which of the following describes what happens to the center of mass of the object Earth system as the object falls downward towards the Earth? Here's the whole idea. This is our system. These forces are internal. They're forces between objects in our system. So the center of mass then must not move.
Yeah.
Okay, the center of mass must not change. We cool with that?
Yeah.
Okay. Only if we have external forces would the center of mass move. Right? An external force would be like me coming and pulling this mass up. That's external. That's outside of my system. The Earth mass system, I am external from that. I apply an external force to lift it up. Now the center of mass has moved. Yes? But internal forces within a system, and it's not something we've really talked about a ton. It's more prevalent when we talk about energy and momentum, which are our next units after circular motion. Okay, but they're on there. It's not something I've addressed, but that's kind of how. So for all three of those examples, the answer is it does not move, because Newton's third law does not change the center of mass of a system because they're internal forces. Is that cool? Shreya, is that good? Okay. Couldn't catch that one on the bounce. All right, what other questions you guys have? I have a student from AP Physics 2 that popped on my my live stream.
Can you just like 2 seconds go over number 8 of chapter 3 concept questions? It's one with the battleships and the like shooting thing.
Yeah. Yep.
God.
The shooting things.
The shooting things that you put on
Those weapons of mass destruction. Yeah, so the idea is we have a battleship. Here's our boat. Okay. Our boat fires 2 shooty things. Okay. One of them, I believe, does this.
Yeah.
Yes. And the other one does this. Right. And they're both hitting other boats, enemy warships, right, in the ocean. Okay. And it says which boat gets hit first. Right? It says which boat gets hit first, A or B. I don't know, but it's the same idea. Okay. So the idea is, remember, this is projectile motion. Okay. The idea with projectile motion is the Y motion is accelerated due to gravity, right? Once there's nothing pushing on it. Once it leaves the gun or the shooty thingy, right? The only thing acting on it, the only force is gravity. And what's true about gravity, that force is constant the entire time. Yes, that's my force. Okay, same idea here. The force, ooh, guys, look. Look. Why does it take an arc?
Because it's square.
Because the force only always points down. Yes? Like if we look at just this part of the motion for this, doesn't it look circular? Yeah?
Oh. Wait.
Because look, what's the velocity? Ooh. What's the velocity in the Y right here? What's the velocity in the Y right there? 0. So you have a tangential velocity in the X, yes? Yeah?
Yeah.
And look, your force is pointing towards the center of a circle.
Oh my goodness.
It's beautiful. It's beautiful. Yes? You guys cool with that? Okay. And here, look. You have a component of gravity. If we think about the total velocity, like my velocity total is there, yes?
Yeah.
Okay, look. There's a component of gravity that's slowing it down.
Yeah.
And there's a component of of gravity that is like this, yes?
That is like what?
Like if we were to take, if we were to take xy like this,
Yeah. Oh, I see.
yes?
Yeah.
There's a component of gravity that is in this direction, which is slowing it down, and there's a component of gravity which is in that direction, yes? Which is causing it to change directions. Because if this is my velocity tangential, and this is my force, it's perpendicular, and it causes it to change directions. Yes? It's that motorcycle question from the conceptual question number 2, yes? There's a part of, if it's slowing down in a curve, yes? Well, as this going up, guess what? It's slowing down in a curve. Yeah? And then it speeds up in a curve. Okay. Anyway, it all goes together, right? It all goes together. What's the question? Which boat gets hit first? Yes? Boat B gets hit first.
Yeah.
Why? Because the time it takes to go up, like if we cut the problem into cliff problems, yes, the time is equal to the square root of 2 delta y over g, right? By this equation. Velocity initial times time plus 1/2 at squared. Okay? Cliff problem, the initial velocity is 0. So then time is 2 delta y divided by g square root. So which of these, so the only thing it depends on is delta y, right? Delta y. Okay? This has a greater delta y, so it's going to take longer for this to go here than it is for this to go there. And that is half the time it's in the air, right? So this takes that much time, this takes less time. Cool with that?
Yep.
Question?
I thought last time we answered this question it was the same time, but I might just be
No.
remembering it. Yeah,
That's a misconception,
Yeah, okay.
right? That's a misconception, okay?
I don't remember the last time we answered this question. So
We've
it's
done this
okay.
question 3 times. We've done this question 3 times now.
Yeah. It's
Probably.
because mine are like-
We did it.
Hey, Nitish.
And then we've done
A
it.
student from last year is on my live stream. FYP, what's FYP?
For you, Dave.
Okay.
That's TikTok. You said no to TikTok.
All right, I don't want to be on TikTok. You guys go with that?
Yeah.
Okay. What other questions we
That's
got?
the same thing for the one where they're all on trees. and-
All on trees shooting. Yep.
Yeah, okay.
The one that hits the ground first is the lowest one. Doesn't matter how fast it's going,
Oh.
right? Doesn't matter because bullet fired and bullet dropped hit the ground at the same time. Okay. They hit the ground at the same time.
What is it? Unit. This is on the AP question.
Yep.
It's unit.
AP classroom.
Yeah.
Okay.
Question 13 on the part A for unit 2 first.
Okay. Let me-
Basically a ball and a launcher.
Okay, unit 2.
Yep, part A.
Okay, let
And
me get there.
question 13.
Unit 3. Unit 2. Part A.
Part A, question number 3.
13.
Yep.
Ooh, I like that one.
Yeah, I was about to say, I can see how you get the answer, but it doesn't fully. It's
A
not.
spring-loaded launcher has a mass of 0.6 kilograms and placed on a platform 1.2 meters above the ground. Okay, so we have a ball, we have a spring, we have 1.2 meters, and this has a mass of
The launcher is
0.6 kilograms.
when the ball's 23.
Oh, the launcher itself.
Yeah.
I'm sorry, that's the mass of the launcher. The mass of the ball,
The launcher fires up 0.3 kilograms.
mass of the ball is 0.3. So half the mass of the launcher. Okay, cool.
Yeah.
The launcher fires a 0.3 kilogram ball and it lands a distance d to the right of the platform. Okay, so it lands some distance d, right? we cool with that? Yeah. Okay. Again, horizontal motion, x motion, is constant, right? It's constant velocity because there's no force acting in the x direction. The only force is gravity. That acts straight down, okay? It's either speeding it up or changing its direction. Those are the two components of gravity. As shown in the diagram above, which of the following explanation is true? The launcher will not fall off the platform because only the ball receives an applied force. Ooh, okay, so here's the idea. There's a spring here, yes? This applies a force this way on the ball to accelerate it, to cause it to start moving.
Yeah.
It applies that force for a very short period of time. It then is traveling at some velocity, and that's why it flies, yes?
Yeah.
The launcher pushes the ball. Action.
Yeah.
Reaction. The ball pushes the
or the
launcher. So there's also a force this way pushing that way. Yes? Which one has a bigger acceleration? Acceleration of the ball. Let's just write it like this. Acceleration of the launcher, acceleration of the ball. Which one's bigger?
It'll be the launcher, wouldn't it? Or sorry, wait, the acceleration is the ball.
Remember, acceleration is force over mass.
Yeah.
Yes?
Just got smaller mass, so it's not good.
Smaller mass, equal force,
Oh.
bigger acceleration.
Yeah.
Yes? Here's where Newton's third law gets everybody. The forces are the same. The result is different. The result depends on your mass.
So they're the same mass.
Right? When you fire a gun, right? When you fire a gun, you shoot a very small bullet. The gun pushes the bullet forward at 400 miles an hour. Yes? The bullet pushes the gun backwards, not at 400 miles an hour, but less acceleration backwards because the mass of the gun is so much bigger. That's why there's a recoil. The bullet pushes the gun pushes the bullet. The forces are the same, the reactions are different, or the results are different, right? When a car is driving down the road and it hits a bug and the bug splatters on the windshield, which is a bigger force, the force on the bug or the force on the windshield? They're the same.
Yeah, oh.
But the bug dies.
But the windshield is like
The windshield is a bigger mass. So the results of the forces are different, but the forces are the same. Okay? Here's what this says. The launcher will not fall off the platform because only the ball receives an applied force. And the launcher will fall off the platform and land d/3 to the left of the platform because the mass of the system is 3 times the mass of the ball.
Oh.
So it's talking about this distance here. Right, so d/3, which I don't really like right away because the mass is twice, yes?
Yeah.
The launcher will fall off the platform and land d/2 because the launcher is twice the mass of the ball. I like that one better.
Yeah.
The launcher will fall off the platform and land d to the left because the forces are the same for both, right? So see what it's trying to test you? Like, yes, the forces are the same, but the results are different, right? And because the accelerate, like, and this is that prime example, this now is acceleration over 2m, yes? So my acceleration is half.
Yeah.
So my velocity is half. So my distance is
d/2.
half.
So the
Yes.
answer was the one just before the last.
Yeah.
Yes.
Yes.
The launcher, that's what I would say. I don't know what their answer is, but that's what I would say.
Yeah, d/2.
Okay.
Really quick.
Yeah.
This first one, I can't remember.
Don't worry about it. It's just all about inertia. The first one where you pull it, we never went over it. The idea is, it's really cool actually. If you pull it very quickly, the bottom string breaks because the mass resists the motion. If you pull it very slowly, the top string breaks because you pull it because it's not resisting the motion. It's like the tablecloth trick, right? If you pull very quickly and you don't apply a force for a long enough time, because things want to stay doing what they're already doing, it does that. If I pull quickly, I actually break the lower string. If I pull slowly, I break the top string. We never went over it. It's not really that big of an issue. Okay?
Inertial mass. What is that?
I do.
Okay, you have to go to the office.
Inertial mass?
That's
No, I looked for
We should
mine.
have said, or like,
Teachers have
it was.
We'll talk about it when we get to graph, when we finish up circular motion. Inertial mass is the idea that like even in outer space, I have a resistance to something moving me, right? Where gravitational mass is more of like the weight that I have. So even if I'm in outer space and things are weightless, it's still hard to move something big because it's still big. It has a resistance to that movement.
Gotcha. Okay. There was a couple questions in the safety class from that had it.
Yeah, we haven't talked about it quite yet, so don't worry about that. Cool. So, people online, any questions? All right. If you guys have questions, stick around. Otherwise, good luck on Thursday. And I'll see you guys next week. I got so many things to do.